Hello everyone, welcome to the 8th lecture of the course Statistical Thermodynamics. The topic of this lecture is a review of classical thermodynamics, specifically the Carnot cycle. The Carnot cycle is a thermodynamic cycle which was proposed in 1824 in the context of obtaining an understanding of the maximum efficiency of heat engines. It has stood the test of time for successfully providing an upper limit for the efficiency of any heat engine. And that is not all. The Carnot cycle gives another major insight. It motivates the concept of entropy. We will discuss both these aspects of the Carnot cycle. In the present lecture, I will discuss the maximum efficiency aspect, and in the next lecture, I will discuss the entropy connection. In an engine, we typically burn fuel and produce heat. At its core, an engine uses heat to produce work. So, schematically, we could draw an engine like this. What we see here is that there is a heat source like a hot gas or hot steam, and that flows into this engine and the engine does work. The way we have represented this engine, it looks like all the heat is converted to work. This is certainly desirable, but experience shows that this is never the case. As you know, the engine in a car or motorcycle gives off hot exhaust gases. So clearly, there is some heat leaving the engine. The engine can be more accurately represented schematically like this. Here, TH represents the temperature of the so-called hot reservoir, which in the case of an automobile engine is the temperature of the fuel-air mixture after combustion. Tc represents the temperature of the so-called cold reservoir, which in the case of an automobile engine is the temperature of the gases exiting the engine. The reason these are called reservoirs is that their temperatures are constant. In the case of an automobile engine, these temperatures are constant, assuming the flow of the fuel-air mixture is constant. We see in the schematic that the engine is taking heat at a high temperature, doing work, and giving off some heat at a lower temperature. Now, the question we ask is, how much of the heat flowing into the engine can be maximally used to do work if we do a really perfect job of designing and implementing the engine? In other words, can the efficiency of the engine be made 1 if we have absolutely no frictional or other losses? And if not 1, how close to 1 can we get for the efficiency? Let us define efficiency. The work done in an engine is W is equal to Q hot minus Q cold. We take the absolute values so that we don't have to worry about the signs of these heat absorbed and heat expelled. The efficiency, which we'll denote with eta, is equal to work done divided by the heat absorbed. That is Q hot minus Q cold divided by Q hot, which is equal to 1 minus Q cold divided by Q hot. Karnaugh explained that efficiency of 1 is impossible for a heat engine, and there is an upper limit to the efficiency which depends on the temperatures of the hot and cold reservoirs. In his arguments, he used the postulate that heat cannot flow from a cold body to a hot body without the input of work. Let us understand this in detail. Carnot designed an engine which uses an ideal gas, and its working can be represented on a PV diagram like this. The state of the gas is initially this point P1 V1, and it is in equilibrium with the hot reservoir. In the first step, the gas is expanded isothermally and quasi-statically by absorbing heat from the hot reservoir. In the second step, the gas is expanded adiabatically and quasi-statically, whereby the gas reaches the temperature of the cold reservoir. In the third step, the gas is compressed isothermally and quasi-statically and gives heat to the cold reservoir. In the fourth and final step, the gas is compressed adiabatically and quasi-statically, whereby the gas reaches the initial state point and the cycle is complete. The work done in the cycle, as discussed in a previous lecture, is the area inside the loop in the PV diagram and is this shaded region. This arrow represents the heat flowing in from the hot reservoir, and this arrow represents the heat exiting to the cold reservoir. There are a couple of points to note here. The first point is that it is essential that an engine has a cyclic process at its core so that it can continue generating work by repeatedly going through the cycle. A simple expansion of a gas against external pressure, although does work, is not an engine because the gas in that case has not returned to its initial state and cannot be used continuously for doing work. The second point is that the Carnot cycle is reversible. If the Carnot cycle is run backwards, as I will denote by the red arrows, then in effect heat is transferred from a cold to a hot body by doing work. This is heat flowing in from the cold reservoir and going to the hot reservoir, and this is enabled by work being done on the system. This is a Carnot refrigerator. Let us now obtain an expression for the efficiency of the Carnot engine. The heat absorbed from the hot reservoir QH is equal to minus W, because this is an isothermal process and the change in internal energy is zero. So from the first law, heat absorbed is equal to the negative of work done, and the expression for work done in an isothermal quasi-static process we have derived is equal to nRTH ln V2 by V1. Similarly, the heat expelled to the cold reservoir during the isothermal compression is equal to minus W is equal to nRTC ln V4 by V3. We have just seen that the expression for efficiency is equal to 1 minus Q cold divided by Q hot, and that is equal to 1 minus this expression here divided by this expression. The only thing to note is that the expression for Q cold as written here is negative because V4 is smaller than V3. So to write the corresponding positive value, we will switch the V3 and V4, and we can write this efficiency as 1 minus Tc ln V3 by V4 divided by Th ln V2 by V1. Now we recall the idea that in an adiabatic process, the volume and temperatures at the initial and final points are related. In particular, for a monoatomic ideal gas, we have V2 Th to the power of 3 by 2, which is the volume and temperature at this point here, is related to the volume and temperature at this point like this. This is equal to V3 T cold to the power of 3 by 2. Similarly, if we consider these 2 points, P1 V1 TH and P4 V4 TC, we have V1 TH to the power of 3 by 2 is equal to V4 Tc to the power of 3 by 2. Dividing the above equation by the bottom equation, we get V2 by V1 is equal to V3 by V4. That is, the ratio of V2 and V1 is the same as the ratio of V3 and V4. Substituting here in the expression for efficiency, the ln terms in the numerator and denominator cancel out, and efficiency becomes eta is equal to 1 minus simply Tc by Th. We can see from this expression that the efficiency of a Carnot engine is always less than 1, and it approaches 1 as Tc approaches 0, or the cold reservoir approaches the absolute zero of temperature. We will now prove that the efficiency of the Carnot engine is the most that is ever possible of any engine. In other words, this expression gives the theoretical maximum of efficiency for any engine that can be constructed to operate between two different temperature reservoirs. Our argument to prove that the Carnot engine is the most efficient engine possible hinges on the idea that the Carnot cycle is reversible. That is, it can run the opposite way and use work to transfer heat from the cold to the hot reservoir. Importantly, the quantities QH, QC, and W are numerically the same, whichever direction the engine is running. So, exactly the same amount of heat that is absorbed from the hot reservoir is returned to it when the cycle is reversed. Let us prove that the efficiency of the Carnot engine, and in general any reversible engine, must be the maximum theoretical efficiency of an engine. Consider another engine A whose efficiency we will suppose is greater than the Carnot engine. Suppose engine A and the Carnot engine are scaled so that the work output of A in a cycle is equal to the work input to a Carnot engine running backwards, and suppose they are clubbed together as shown here. The work output from A is used to drive the Carnot engine backwards. If efficiency of A is greater than the efficiency of the Carnot engine, then using the definition of efficiency, this implies that W divided by QA hot is greater than W divided by Q Karnaugh hot, which implies that Q Karnaugh hot is greater than QA hot. The net heat extracted from the low temperature reservoir is this quantity minus this quantity. That is Q Karnaugh hot minus W minus of QA hot minus W. we see that this net heat extracted is positive. This is also the heat delivered to the high temperature reservoir, which we can get by subtracting this quantity from this quantity. This implies that there is a net positive quantity of heat extracted from the low temperature reservoir and delivered to the high temperature reservoir. And it further implies that the effect of this self-contained machine is that it transfers heat from the cold to the hot reservoir without any external work. This is in violation of the postulate that heat cannot be made to flow from a cold body to a hot body by a device which does not need any work input. This implies that the initial assumption we started with, that the efficiency of A is greater than the efficiency of the Carnot engine, is false. It is therefore impossible for an engine to have a greater efficiency than the Carnot engine. There are a few points you should note. The first point is that it is perfectly possible for an engine to have a lower efficiency than the Carnot engine. Please check for yourself what is the net heat flow in the present setup if A has a lower efficiency than the Carnot engine. The second point is that the theoretical maximum of efficiency of any reversible engine is the same and is equal to the Carnot engine. We have not used the specifics of the Karnaugh engine in our above discussion, only the fact that it is reversible. So the statement may seem obvious. But you can also prove it explicitly by coupling the reversible engine A with the Karnaugh engine in the opposite way. That is, the Karnaugh engine drives the refrigerator A, and you can use similar arguments to what we have just done. We have seen in this lecture that the maximum efficiency of any reversible engine is equal to that of the Carnot engine and is equal to 1 minus the ratio of the temperatures of the cold and hot reservoirs. In the next lecture, we will discuss how the Carnot cycle suggests the idea of a new property, namely entropy. See you for that.